We had boundary conditions, inlet, outlet, the blood properties. We learned how can we create geometries using ANSYS model. So going to geometry, design modeler, we imported geometry already existing. We created the shroud here, inlet and outlet ducts. We carried out Boolean operation to subtract it. After that, we created mesh. In that category, first we created the name selections for inlet, outlet, walls, and then we created interfaces at the inlet and the impeller shroud, and at the outlet and the impeller shroud. After these interfaces, we created mesh, and then we took it to the fluent solver. And in the fluent solver, we gave the rotational velocity to the rotating parts, and we ran the simulation under MRF. After MRF, we used transient simulation, and we managed to get the sliding mesh model of this running. And after we ran it, we obtained the sliding mesh results. So this was the process that was done yesterday, just to make you aware of the process of simulating the flow in the ventricular assist device. The main aim behind this is that you can calculate both the global and local performance parameters, and you can see whether the system is working properly or not. In today's class, we will understand the performance measures, how can we estimate the performance of the ventricular assist device, and how can we diagnose the problems in the ventricular assist device. What happens when there is a problem with the ventricular assist device, and we'll again use only computational fluid dynamics for that particular purpose. Okay, so this is what we are going to do now. Yesterday, we'll start from here. You have done the analysis, and you have got the results. Now, how do we get data that will tell us about the performance of the system, performance of the ventricular assist device? So, in this particular case, we have analyzed the performance of axial flow ventricular assist device, which is allowing 0.08 kilograms per second of blood to flow at 9500 revolutions per minute. And what we are doing is, we have now to consider systematic investigation to obtain the flow features within the VAD, and we would like to obtain the performance curve for the ventricular assist device. Okay. Now here I want to give you some brief information. Now VAD, ventricular assist device as a whole, we can analyze in two manners. Okay. So global performance indicators, local performance indicators. Now global performance indicators, mostly in lab, what you can see is you have a VAD. You can measure pressure across it, you can measure the flow rate across it, isn't it? And you can see how much pressure rise it provides. So for a given geometry, how much pressure rise to blood it is providing, that you can do experimentally, isn't it? You don't need CFD for that matter, because you can see using experiments. If you have a good lab, people will test it, and then if it works, that is what is mostly done. The new thing that you can do is to locally see how the flow is, because the interaction between blood and the ventricular assist device is happening at the local level, isn't it? The shear rate, wall shear stress, effect of rotation on the blood properties, effect of blood on the performance of the VAD will take place at the local level. So global level indicators are fine as far as the overall performance is concerned, but if you want to really carry out detailed analysis of the effect of VAD on the blood performance or blood on the VAD, for that you need to carry out local performance indicators, and that is where CFD becomes very, very important, because globally you can do it using experiments as well, but locally to do it using experiment is very, very difficult. Then you have to have instruments that can measure flow inside the VAD, which it becomes very, very difficult. So in this particular class, I would like to explain both these features, global performance indicators and local performance indicators. Now, so here, when I say local performance indicator, what do I mean? So like for example here, this figure we discussed yesterday. So here, you can locally see how the flow is taking place, isn't it? On this plane and on these three planes. There is no way experimentally you can find this information. Can you? You cannot find this information experimentally. Again, locally you can create different sections and you can see on different sections how things are changing. That you cannot do experimentally otherwise. Only using CFD you can get this particular information. So this is an example of local information that you can get. Again here, locally you can see how the flow is taking place. There is no way of doing it experimentally otherwise, because experimentally you can do pressure drop measurement, flow rate measurement, but local velocity measurement, unless you have especially designed equipment like example particle image velocimetry and other things which can do it, but that is very, very complicated. Using CFD you can do it very, very easily, okay? Like this type of thing. If you look at this one, I'll again give you an example. This is line 2. This is the line 2. Along this plane, this is the velocity profile. What does it say? At y is equal to 0, it means here the velocity is 0.35 meters per second. But if you go close to the wall, velocity is becoming 0, isn't it? Now slope of this line will give you the boundary shear, okay? If slope is higher, boundary shear will be higher. If slope is lower, boundary shear will be lower. So this velocity profile tells us a lot about the shear the blood is subjected to, and that shear is what causes the breakage of red blood cells, the effect of boundary shear wall shear can have on thrombosis and things like that. So this information you can only get through CFD. You cannot get this information through experiments, can you? No? Can you get these experiments? Very, very difficult unless you have very, very sophisticated equipment worth millions of rupees. But more important is here, line 3, see here. The regular velocity profile has completely changed here. This is the velocity profile in this part and in this part. You can see how different the velocity profile is. So here, this is the velocity. You can see it is reasonably symmetric on the two sides, and in this part there is no flow because there is solid body here, isn't it? There is solid body. That's why you are not getting any value here. From here to here there is no value, okay? Why? What is the reason? Why don't we have any value here? Here to here? Am I speaking some other language? Because this is a solid body. You cannot have blood flowing through this, can you? Blood is only flowing through here, isn't it? That's why you have velocity here, this part and this part. Here there is no velocity. So this corresponds with the inducer, isn't it? Likewise, line 4 here, this line 4 again here. You can see now this velocity profile is like this. Here. Why do we have non-zero velocity here? It is 0 here. Why do we have non-zero velocity here? In this part, velocity profile is like this. In this part, velocity profile is like this. Why? It is because impeller is rotating. So this part corresponds with the impeller, but impeller has a velocity, doesn't it? And because no slip condition has to be maintained, you have non-zero velocity here. You have non-zero velocity here. Whereas here, this part is not rotating. So you are getting zero velocity here and zero velocity here. Only this part is rotating. Likewise, if we go to line 5, that is here, you have a velocity profile of this nature. Okay? So velocity profile at this particular point. So locally, this type of information you can get only from CFD or from very sophisticated measurements that you can take. Otherwise, this type of information will not be available to you. So now, if you just plot the gradient of these, okay, just plot gradient of this and you can see the shear stress distribution everywhere. So everywhere how much shear stress is acting on blood you can calculate, and what effect it will have on the blood properties you can calculate. Okay, making sense? Any questions on this? Can you write half a page to 1 page on these 5 figures? Making sense? This is what we do when we write papers and things like that. That how the flow is taking place, flow is coming from here and is going there. Does it not move forward? Yes. अच्छा इसका वो नहीं है क्या? था तो लेकिन पता नहीं कहाँ चला गया. Anyway, let's leave it. So what I'm saying is, when you analyze the flow through this picture gives you limited information, but this picture gives you lots of information, doesn't it? This picture gives you lots of information. We can say that when flow is entering, velocity profile is like this, with peak velocity here, zero velocity here. As it approaches the flow here, you have zero velocity here, zero velocity here, zero velocity here, zero velocity here, and peak velocity somewhere here. Peak velocity somewhere here. See this peak velocity somewhere here. As we go further here, then we get peak velocities at the two walls. As we go further here, we get velocity profile like this. Again, peak velocity is somewhere close to the wall. So the wall shear stress will be higher in this region, in this region, in this region. So that will dictate where the problem on this vertical ventricular assist device may occur. Okay, making sense? Any questions? No? And then these are the overall performance parameters which you can get from experiments if you wish, because you can put pressure measuring device that can tell you how much pressure rise will take place. You can use power measuring device to see how much power it needs, and you can measure input power and output power, and you can calculate the efficiency. So these things you can measure. Now locally, if you see, you can calculate the wall shear stress. It gives you wall shear to find shear in blood, to calculate it yourself or ask flow to do it through the velocity gradient to calculation. But you can get, this is wall shear stress, means shear stress at the wall. Okay, see how the wall shear stress is higher here and higher here. So wall shear stress beyond a certain value can cause lots of problem in the instrument. Things like thrombosis can happen, and the blood clots can form here, and that can really damage the entire system, including the patient's health, and that we can see from here. We can see turbulence intensity. It's not very significant in this particular case, but still you can get turbulence intensity term. Things like vorticity magnitude, rotation in the blood, and the positive Q criteria, which is defined as half of vorticity magnitude square minus the strain rate square, and if it is positive, it means the vorticity is higher than the strain rate, and this indicates the vortex shedding phenomena. So you can see where vortices can be shed, that you can see from this particular figure, and so here vortices can form, and that can lead to a number of undesirable happenings, so that we can find here. So this is in general the performance analysis. Now I want to establish, this is qualitative information about the performance analysis. Now I want to carry it out quantitatively, so that we can establish the relationship between various parameters. So here what I am doing is, in this particular case, the flow rate is 0.08 kilograms per second, and the VAD is running at 9500 revolutions per minute. Now I want to run it at different conditions and see what is happening. As I mentioned to you earlier, I'll be using two approaches: global performance indicators and local performance indicators. Global performance indicators you can verify through experiments. Okay, you can have experiments and you can verify it whether these simulations are right or not. That is what you call as validation. Okay, so you can use experiments and validate your results. And local performance indicators gives you the more detailed about the flow. Okay. So in this particular case, I have taken data from this paper, validation of an axial flow blood pump, computational fluid dynamic results using particle image velocimetry. So they have used both CFD and particle image velocimetry. So I have taken that data and I have run this simulation. So just to establish the effect of speed, I have taken two speeds, 9000 and 9500. The previous results were 9500. So I ran it at 9000 and then I took 5 flow rates, 3.01 to 7.01, and almost same flow rates I took at higher speed, and the mass flow rate varied from 0.0522 to 0.122 kilograms per second in both the cases approximately, and the pressure outlet was varied from 17,025 to 8359 and 14799 to 6639. So this is the data that I took to run the simulation. Okay. Any questions so far? No? Any questions? No? Making sense? No? So this is the data that I have taken to find out the, to establish the dependence. And let us see, this is your performance curve. You can see here, this is the lower speed curve, this is the higher speed curve. So at 9000 RPM, you can see delta P decreases as M increases. This is typical pump curve, isn't it? Typical pump curve is like this. And we can see the effect of speed at higher speeds. For a given M, delta P is higher, but the trends are almost similar. Okay. In your case, you can run it over a wide range of speed conditions, like you can run it from 5000 RPM to 15,000 RPM, take 5 different values and then see how the performance is there. Okay, so then you can do it. So as the mass flow rate increases, differential pressure decreases. What does it mean? If your volume flow rate is high, pressure rise is smaller. Okay, so you have to have an optimum volume flow rate and optimum pressure rise. At a very small volume flow rate, pressure rise can be very, very high. So you have to, your control system must be strong enough to take the required blood flow rate and pressure requirements into that. So it has to be reasonably intelligent in this regard. Any question on this? In your undergraduate classes, you must have seen it. Delta P against Q. Praveen, am I right? Next, the power input. Again, power against mass flow rate, you can see the power curve is like this. There is very small difference between the two speeds, although like at higher speed you need higher power, at lower speed you are having lower power. So if you run pump at higher speed, the power requirement becomes higher. Okay, power requirement becomes higher if your speed is increasing. Efficiency. This is your efficiency curve, and you can see that typically efficiency, peak efficiency is at about 0.083 here. So your system will work most efficiently at about 0.08 kilogram per second, and the typical efficiency we are getting is about 40%, 30 to 40% here. So these are our global performance indicators. Okay. Any questions on this? No problems? So this is our global performance indicators, isn't it? So you can calculate output power, input power, efficiency. So all these things that you can do experimentally, you can do here, and you can verify the results through that particular process. Okay. You are comfortable with it? Or any questions you have? Anything on this? Do you understand the physical meaning of these terms? Efficiency is ratio of output power to the input power. Okay. So this is ratio of output power produced by the pump to the input power to the pump. Okay. So this is efficiency, and that is highest at 40%. Okay. And that is at 0.02, 0.08 kilograms per second. Right. So this is the global performance indicator. Let us come to the local performance indicator. So what I have done here is, I have shown you three things, two effects I am trying to show you here. The top two are same speed, different flow rates. And first and third are same flow rate but different speeds. So if you look at this, the static pressure, how static pressure is varying. If you look at this, the difference of static pressure at 9,000 RPM at 3 liters per second and at 7.01 liter per second. If you see the difference in the high value and the low value is very, very small for this case as against this case. Difference, if you see this value here, it is somewhere here, this value is somewhere here. So difference is in about 4 to 5,000. But if we take this value, this is somewhere here, and this value is also somewhere here. Okay, so this difference is very small. What does it mean? It means that when the flow rate is higher, the pressure difference is small. So as the flow rate increases, the pressure difference becomes smaller, and this is same as this figure. This figure. As the flow rate is higher, the pressure rises smaller, isn't it? So same thing we are seeing there. Now, second one, the third one. If I take this and this, if you look at this, difference between this and this and this and this, in this case you will find that this difference is slightly higher. This is slightly brighter, isn't it? So we are somewhere here, whereas this is somewhere here. On this side, it is almost identical. The difference of these two is higher here than here. So what it means? It means as the speed increases, pressure difference increases. Whereas as the flow rate increases, pressure difference decreases. So here in this particular case, as the flow rate increases, pressure difference decreases. But as the speed increases, pressure difference increases. Okay? Any questions please on this? Coming to local flow analysis. Now, for local flow analysis, what we have done is, we want to see how pressure is varying along this line here. How the pressure is varying along this line. Because if you take this part, this is okay because most of the part is covered by this blade. But if you take this part, the blood is flowing in this part continuously, and the blades are affecting the flow, okay, which is causing pressure to change here. So I want to see how flow takes place in this part. Okay, so that is why I have created this line here. I have created this line here, and I am seeing how pressure is varying along this line. This green line you can see here. I am seeing how pressure is varying along that line. Now you can see how pressure is varying. So what I have used a term which is used in fluid mechanics, that's known as pressure coefficient, and pressure coefficient is defined as P minus P in over half rho V in square. I think yesterday I mentioned about this. Didn't I? Did I mention about this? Yeah, here. P local minus inlet pressure over half rho V in square. Now P in is inlet pressure, V in is the inlet velocity of the square is direct because flow takes from here. P in. As we go along, pressure is increasing, isn't it? Each part contributes. So how am I doing that? I am calculating P local along this direction, P local, how P is increasing with respect to P in. So at start, what is the value? 0, because P in is P local. This is 0 here. And as we go along this length, this starts to increase. This increase is smaller here, and suddenly it increases here, here and here. So now we will see the interaction now. See. कुछ खास बात? Please delete this part. No, I think I have forgotten that thing somewhere. Oh, it's there. Okay. And wonderful. Now, I would like you to just put a bit of attention on this part, okay? Very, very. Here, what is happening? I am plotting CP along the length of the impeller, okay? So here, I am plotting P in from here along the length here. So let's see what this system does on pressure. This is what we are trying to understand, okay? So here, this is the straight line part, okay? This is your straightener part. This is your straightener part. You can see at, let's take one value, 9000 RPM. So at 9000 RPM, pressure starts to rise slightly here because of the helix available at straightener. Then in the first part, it goes up, goes down, goes up, goes down, goes up to this particular point. So in the impeller part, pressure, in this part, pressure is rising. And then we have a diffuser part. So in diffuser part, what is happening? Pressure, sorry, this is at the end of the impeller, then it is going down and becoming constant at that particular point. So this is the impeller geometry here. And you can see how the impeller geometry is affecting the pressure rise. It goes to maximum pressure up to here, and then it becomes stable at this particular point. So the total pressure rise is this minus this. Okay, this is the final pressure. After this, this is the initial pressure, and this difference is the pressure rise by the impeller. Okay. Now, same thing, if we are running it at high speed, 9000 RPM, it goes here. Okay. It is 9500 RPM, it is going here. So pressure rise has slightly increased as seen in this figure. So this is a very important figure as far as you are concerned, because this shows the effect of design on the pressure rise. You can take it in different parts, 1, 2, 3, 4, 5 parts, and you can see in which part you are gaining pressure, which part you are losing pressure, and why. Okay. So which part you are losing more pressure, in which part you are gaining pressure, this you can see from the figure as shown here. Okay. If you change the geometry, you make a different type of figure. So this effectiveness of the geometry, effectiveness of the impeller that you have for the ventricular assist work. Okay. Any question on this? If I ask you to write half a paragraph about this, can you write? How many of you will feel comfortable writing it? No? Can you write half a paragraph? What is first sentence? Anyway, it's okay. I understand you can write. So this is here. This is how this information you cannot get from anywhere else, can you? This information can be given to you only by CFD. You cannot get this information from somewhere else. So this is locally we can see. Praveen? Okay? Making sense? Now let us see some velocity components. So we have looked at the pressure, which is very important thing in this case. Now let us look at the velocity. Again, what I have done is I have taken three cases here. One is at 9000 RPM, 3.01 liters per minute, 9000 RPM, 7.01 liters per minute, and then 9500 RPM, 2.99, which is approximately 3.01 liters per minute. Now, if you look at the axial velocity, the trends are almost similar. Although the velocity magnitudes have changed slightly, but they look almost similar. You can see the flow structure here. Velocity is becoming slightly higher in these regions, here, here, and here. But the flow structure remains same. At higher speed, there you see higher velocities near this region, indicating that probably the axial velocity are higher in this part. But keep in mind, near the impeller, the tangential will be like this. Okay, there you can see whether flow is accelerating or not. Within this part, the tangential velocity will also become very, very important. This shows the radial velocity, means velocity radially means this direction, going from here to here. And you can see these velocities are very, very small. These velocities are in this range, very, very small velocities. So radial component is, so blood motion in this direction is very, very. This is the tangential velocity, which is very small in this part, but you can see near the impeller, where it is rotating, this velocity is very high, isn't it? In the impeller, so what is tangential velocity? If this is VAD, this is tangential velocity. Okay, so this is axial velocity, this is radial, this is tangential velocity. So because this is rotating, tangential velocity is high here, but this velocity is almost zero here because this part is almost stationary. So this shows the rotation of the flow near the impeller. This is important because all these will affect the blood structure. Blood structure can be affected by three-dimensionality of the velocity flow. And now this is what I like. This shows locally when you run flow at different positions, how it affects the flow pattern locally. Again, I have taken 4 lines, line 2, line 4, line 5, and line 3. Again, I think I am taking the same type of thing here. So at the inlet, line 2, line 3, line 4, and line 5 thing I am taking. Now at the entry, you can see it is very well developed velocity profile at the inlet. At higher velocities, at 9000 RPM, at 9000 RPM, the velocity profile is almost typical. At 9500, there is hardly any change at the inlet, because at inlet there will not be any change. But at higher flow rate, the gradient is much higher here, at the peak velocity is much higher here. So this is how the velocity profile at the inlet would be. Okay. Feeling bored? What is the issue? Asking any question? There is something. Okay, so this is how the flow velocity is at the inlet. When we go to line 3, near the impeller, you can see the velocity has become very high at high speeds here. So at high speed, the shear rate in this part will be very, very higher. You can see here and you can see here. This is the two end. Whereas at 9000 RPM at two different speeds, again the flow pattern seems to be changing here at the between the straightener and the wall. At the exit again, you can see velocity profile has drastically changed at two different speeds and two different flow rates. You can see the flow pattern has completely changed, and this indicates not only the maximum velocity magnitude has changed, its location seems to be shifting as well. And on the two sides, we are seeing two different patterns. Why? Because the helix pattern is not same. So helix pattern is affecting the flow on the left side and on the right side. And at the exit, again, the well-developed velocity profile pattern has been created. Now this indicates one thing, that because velocity profiles are different at different speeds and different flow rates, the shear stress will be different. And in each case, because shear stress is different, it will affect the blood in a different. Okay? Is it making sense? All of you making sense? Any questions you would like to have? No? Now, I was talking about wall shear stress. So you can say the magnitude of wall shear stress effect of speed slightly higher here, or effect of flow rate definitely higher on this particular part. Turbulence intensity, effect bigger zone here, effect of flow rate almost identical, although the magnitudes are different in the two cases. Vorticity magnitude, again the vorticity patterns is affected by the flow rate, higher vorticity here, and in this case higher speed is again the vorticity is near the blade. The positive Q criteria is higher at higher W values and higher flow rate values as well. So there is more chances of vortex shedding at higher speeds and higher flow rate. So this is how performance of the impeller for a particular application. Okay, is it making sense? So I would like each of you to ask one question at least now on the performance. Question, each of you.
Velocity profile and characteristics are related. With increasing velocity will cause change in wall shear stress more.
Yeah, because what you see here in this particular case, this velocity is higher. So if I calculate slope of this line, will be higher as compared to slope of this line. So the velocity gradient will be higher in that case. Wall shear stress will be higher. So you have to find the comfortable range of speeds and the flow rates over which a VAT can work properly. Because if shear stress values are beyond, for example, 7, then this can happen.
And damage to that.
Yeah. So for patient health, if it is beyond 7, that can be dangerous. So that is what we have to. And it can happen anywhere. Here, within the device, it can happen anywhere here. So we have to know locally what is the wall shear stress at different particular points. Mostly it is okay, but you can see pockets here, but it's very, very high. Isn't it? So you have to do something about it. If you just leave it there. Okay, Praveen, any questions on this? This is your research topic? No? One question at least. One question at least, all of you. You know, you understand Q criteria. Q criteria is the half of the vorticity minus strain rate, square minus strain rate.